button.
All right, here we go.
Hello, everybody. Good morning and welcome to this session of the University of Oregon Undergraduate Research Symposium. We're excited today. We have four presentations in our session, which just has the title, let's make sure we get it right, Asteroids, Algorithms, and Arctic Glaciers. So if you want some, good morning and welcome to this session of the University of Oregon Undergraduate Research Symposium. We're excited today.
You might want to close that if you have that open on another window, Scott.
I'm sorry, hold on.
You've got YouTube, no worries.
If you want some, what do I have open? There we go. My bad. Thank you. Hi, everybody. Technical issues, old guy using the internet. So the point is, welcome to our session. I could hear myself and I absolutely froze. I'm like, oh my God, that's what I sound like? That's terrible. So anyway, sorry about that. But welcome to the session. We've got four presentations coming at you here today in our session called Asteroids, Algorithms, and Arctic Glaciers. And what I wanted to say is that if you're ready for some diverse topics in some interesting science fields, this is the session to be in right now, right here. And as an added bonus, we have a wonderful international flair where we have some colleagues from Japan are dialed in and are going to help us present later today. And so look, how this is going to work is each of our student presenters has about 15 minutes to talk about their project. And then we have some time for some Q&A. We have some Q&A after each poster presentation. And at the end, we'll probably have a few minutes too. So feel free to ask questions along the way. We have a chat where you can submit the questions through the chat. And we'll see them and we'll feed them to the presenters as we have a moment. And so thanks everybody for coming, and let's get into it. Let's start with our first presentation. Our first presenter is Jared Knopczynski, who is a Max major. And by the way, Max is an interesting major at UO. It's a combination of mathematics and computer science. And that's something that's fairly unique at UO, combining these two very interesting topics. And Jared is going to give us a talk and show us a poster about a multitask weak supervision framework for internet measurements. And so you can see this is a combination of those two topics. Jared, welcome. How are you doing this morning?
I'm doing pretty well. Excited to show off what I've been working on.
Excellent. So what year are you in at UO?
I'm a junior.
A junior. There you go. Nice. So you have another year to continue on after this, and good deal. So how'd you like to present for us here for a few minutes?
Sure thing.
Excellent. Take it away, sir.
Awesome. Let's see. See that all right?
We can indeed. Well done.
Great. All right. Well, hello, everyone. My name is Jared Knopczynski, and I'm here today to talk about my research on the efficacy of machine learning in the context of internet measurements. I've been working on this project since late October of last year with my advisor, Ram Durarajan, as a part of my computer science and honors college theses. And actually, just yesterday, we submitted our findings to the AMC Internet Measurement Conference for 2021, hopefully to be reviewed and subsequently published there. But before I dive too much deeper into that, I'd like to give some background on my topic of research. So there we go. So as you all know, the internet is an incredibly complex mechanism that allows the sharing of information over incredible distances at incredible speeds. However, it's not without its flaws. You've undoubtedly experienced some of these issues firsthand, especially in this era of remote education, where slow connections can inhibit our productivity, and network attacks can leave important digital resources vulnerable or inaccessible to people who need them. Furthermore, attacks like denial of service attacks can disable or disrupt vital infrastructures that we depend on today. And as the volume of traffic on the internet continues to grow at extreme speeds, the successful moderation of these connections becomes more and more difficult for human agents to perform. So, network operators are turning to machine learning solutions to identify and address these problems programmatically. However, there are a number of issues that prevent the widespread adoption of machine learning techniques in networking domains with the current state of the art of the field today. The first issue that I'd like to address is the lack of labeled training data that machine learning models possess. So to train a machine learning model, we require large quantities of information to effectively tweak and tune the parameters of a model. And the typical solutions for obtaining such data sets that work well in other fields like crowdsourcing or other distributed sources are ineffective in networking, as the proper classification of internet measurements requires a level of domain expertise that most crowdsourced labeling resources just don't possess. For example, if I showed you this and asked you to tell me which one was a cat or a dog, you could probably do that pretty easily. But if I showed you a snippet of network data, such as this, and asked you to tell me which of these points represent a distributed congestion event, you might have a little bit more difficulty. So, to construct labels for large quantities of network data, researchers have developed a technique called weak supervision, where they leverage operator expertise in the form of labeling functions to translate domain heuristics into actual concrete labels for quantities of data. And however, as network tasks are often multitasked in nature, meaning that to effectively classify or categorize a specific type of event or feature, they need to identify multiple component characteristics. So that leads us into the next problem, which is the prohibitive training times of machine learning models. Imagine if you were a network researcher and you wanted to construct a machine learning model capable of classifying congestion on your network. The model you construct might look in abstract something like this, where your input data, your observed input data, is fed to a number of hidden layers that can train and optimize themselves for the specific classification task at hand. And this works well enough in this given context, but now let's say you wanted to add a loss classification system to detect outages or drops in the connection around the same events. You would likely expand your model to look something more like this, which is, again, not too complex, but now you're also repeating a lot of the same processing legwork that you did previously across these two different classification tasks. And as I mentioned, many internet measurements tasks are multitasked in nature. So to successfully execute and classify them, we need to train multiple models. And as we can likely imagine, when you start to have more tasks, this approach can get ugly pretty fast. Thus, we see that as the number of tasks grows, so too does the amount of time each model takes to train, as it must be independently tweaked, evaluated, and optimized separately from all the different components of the model. And as the number of tasks grows, the potential time and financial costs associated with model development can quickly become prohibitive for the adoption of machine learning techniques. Another issue of note is that in traditional approaches to machine learning, it's unclear how we might be able to leverage similarities across different classification components to improve model performance and accuracy. In network data in particular, these symptoms of underlying features or the patterns in the data may possess significant overlap with one another. For example, on the left here in this figure, we see a brief period of network volatility, likely indicating a sort of noise event, some characteristic feature that is not representative of the broader set of data. Then on the right, we see something more in lines with what we might imagine a congestion event to be, with a sustained period of increased latency. Although it may not be as extreme as the noise period, it still exhibits similar characteristics. This is represented by the sudden change in the round trip time, which is what we measure as sort of the time it takes a connection to both reach a network host and return, the round trip time. And we can see that in the congestion event, there's that same network volatility to a lesser degree. So ideally, we should be able to leverage these similarities to improve our models. But in traditional machine learning approaches, it's unclear how we might be able to do this when we're operating with machine learning components that are distinct, such as this. Lastly, I'd like to address the lack of interpretability of machine learning models. To conduct their analyses effectively, network operators require a certain degree of confidence in understanding the performance and prediction decisions of their machine learning models. But with the black box nature of machine learning systems that we employ today, this is difficult and fundamentally contradicts this need of network operators. So where does that leave us? What if we could collapse a machine learning network such as this to remove the redundant processing and be more streamlined in the addition of novel tasks? And what if we could do it in such a way that also leveraged the capabilities of weak supervision for networking data as well? We envision something like this, a framework to allow the addition of multiple tasks using the same shared hidden layers and information processing setup to share information between tasks, thus improving the accuracy, enhancing the interpretability, and leveraging weak supervision capabilities for internet measurements. And there's a number of sources on each of these subjects separately, but the actual combination of these has really yet to be explored as a field of interest. So we draw on a number of different sources from roughly 3 existing categories, that of internet measurements, weak supervision, and multitask learning, to combine disparate tasks into one cohesive model. And that leads us then into our research question, which is, to what extent can we leverage the similarities in latency data via multitask learning and weak supervision to reduce model training times and improve classification accuracy in the context of internet measurements? Now for our methods. To actually conduct our experiments, we begin by constructing labeling functions, which are, again, simple representations of domain or operator expertise. And then we classify specific features in a multitask method. We developed these classification tasks using Snorkel, which is a framework for weak supervision, and then train a multitask classifier on these classification tasks. To actually evaluate our performance of our models, we compare against equivalent single task methods in prior research, some examples of which are shown in the bottom left here. For our data, we use a collection of time series latency measurements provided by both the K2ARC and RIPE Atlas projects. The K2ARC, in the K2ARC dataset, we analyze over 75,000 individual latency measurements split into 28 different datasets that we train and test on. And in the RIPE Atlas dataset, which we consider an expansion of our initial analysis, we analyze over 2.5 million entries across 100 datasets. Now for the experiments. So to compare our models, we measure the average training time and mean F1 score of each model on each task. The F1 score is basically a measurement of both model precision and recall, granting equal weight to both of these features in machine learning classification. So on the left, we show the results for training our models on the K2ARC datasets, and on the right, we show the RIPE Atlas datasets. First, in the K2 datasets, we see that the single task models on the left here are trained reasonably well to a high degree of accuracy in what in machine learning is considered a fairly reasonable amount of time, which with each task taking somewhere in the neighborhood of 2 minutes to train on an individual dataset. However, when we compare our multitask approach to this, which instead of training each model sequentially, such as the loss, congestion, or noise classification models, we train them concurrently in a multitask classifier. And we note that the amount of time it takes to train is significantly less, nearly over 90% faster than the equivalent single task approach. We also note that the comparable performance was either equivalent or better in all cases. Then we extrapolate to the RIPE Atlas datasets, where we see that the noisier distribution of the inherent dataset made it difficult for the single task models to train to a sufficient degree of accuracy, even on a simple classification task. In contrast, we see that our multitask approach trained to a much higher degree of accuracy, again, in a fraction of the time. And so this is where the results left off on my original poster, but I'd also like to take a moment to discuss the results of subsequent experiments that we conducted after. So in our second set, we then experimented with adding in a change point classification task to the existing tasks we mentioned before, and again retrained on both the K2ARC and RIPE Atlas datasets. On top, we see that the performance for the equivalent datasets on the loss, noise, and congestion models was unchanged for the single task approach. However, the change point classification task was less than desirable when considering its accuracy. In contrast, the addition of the change point classification task to our multitask method actually enhanced the classification accuracy of the other tasks due to the implicit data augmentation and information sharing capabilities of our model. We see similar results, again, just showed on the RIPE Atlas dataset, where again, the noisy distribution of the data made it difficult for the multitask classifier to train to a high degree of accuracy, but it still significantly outperformed the single task equivalent. And again, looks like we see that in the CADA datasets, our multitask classifier was again much faster than the single task methods. And we see again the same results in the RIPE Atlas dataset. For our last experiment, we also explored composing these distinct subtasks into combined classification tasks, where rather than classifying either just loss or just noise or just congestion, we added 2 classification queries or combined tasks, task 1 and 2, on the multitask approach to explore how the information sharing capabilities of the model enhanced the accuracy of such a combined task. We didn't do the same experiment in the single task approach because a single task methodology to this sort of query would involve training a separate task on each of these disparate elements and then taking sort of the worst performance of each of them as a bottleneck for the performance. And we see again the same or similar timing results where the multitask approach trains significantly faster than the combination of all of these single task methods. So where does that leave us? From these experiments, we can conclude that multitask learning is clearly much faster than the single task equivalent and better generalizes to larger, unseen, and more realistic data sets in network use cases. The information sharing between tasks also improves classification accuracy compared to single task equivalents, thus suggesting that MTL, or multitask learning, has the potential to revolutionize how we combat network issues. Multitask learning also enhances the interpretability of machine learning models, making them more viable in network domains, as operators are better able to interpret the results from a multitask classifier that has relationality between tasks rather than distinct single task classification methods. And we believe that weak supervision and multitask learning can be leveraged in other fields as well, likely with similar levels of success. For our future work, we'd like to explore a few different regions of particular interest, namely the applications of ARISE, which is our framework, in other network-related domains, such as detecting denial of service attacks or enhancing network security, or modernizing network management to enable a sort of conversational artificial intelligence tool to enable natural language processing of network operators to more easily and quickly perform network queries on large sets of latency data. Lastly, we'd also like to explore the efficacy of our framework in the context of adversarial examples to both strengthen and make it more robust in the context of an applied setting. But we'll save those for another time. I'm also honored to have been selected for the VPRI Fellowship for this summer, so I'm hoping to continue exploring some of these questions during that time period. So with that, are there any questions from the audience and anything else we'd like to address?
Thanks, Jared. And right on time too. So well done. Thanks for that. Let's give so it's just a second. Well, whether you all like it or not, I'm going to have questions for all of you. And I think as part of the moderator, I feel so fortunate to be in this particular group because I'm interested in all the projects. And Jared, for you, I thank you. I had what's the next steps for the project. So I appreciate the summary slide right from the beginning. I mean, so when you say weak supervision, I mean for the folks who aren't in the field, does that mean that these tasks that you're creating, they're running kind of autonomously, or they're learning themselves? Is that what that means?
Yeah. So in the context of machine learning, there are a few different primary approaches. There's supervised learning methods where the researcher is basically explicitly saying, here are the rules I want you to follow. Here's what I want you to learn and classify.
Yeah.
Then there's unsupervised learning, which is kind of the complete opposite, where we say, okay, here, I want you to figure out the best way to do this. I have no idea what it is. That's your problem.
Right. You're saying this to the computer code.
Yeah.
Basically. Yeah. Mm-hmm.
And so weak supervision is kind of marrying the two and taking the strongest elements.
Yeah.
So rather than having to explicitly define all of the rules, we can use weak supervision to generate weak and noisy heuristics that we say, okay, well, if a data point is significantly higher, if it's much higher latency value than all the rest, that's probably a noise event. So we use kind of these heuristics to apply our labels to a large data set, and sort of the amount of data that we give it enables the machine learning systems to remove the bias and the incorrect values just through the sheer amount of quantity of information.
Right.
So by having those, we are effectively adding some way to leverage operator and domain expertise and relevant knowledge by using and defining those heuristics. But we're also allowing the computer to say, okay, you've given me a lot of information. Let me see what I can do with that. And then let me tell you what I do. And you can kind of go back and tweak and optimize as you go.
Yeah, so in that sense, the weak supervision is really a very, very apt descriptor, because you're giving it some rules, but then you let the computer go off and do the learning when it's there. And of course, one of the advantages of that, I would assume, is of course the speed at which the computer can operate, and it's doing millions and millions of these optimizations and calculations, so can be quite quick, I think, in the learning. Is that
Exactly.
And so I have one more question, a very practical question, and that is, I think we might all have heard in the news recently, there has been a cyber attack where a pipeline, a natural gas pipeline was held for ransom, and are these the type of events that eventually maybe this sort of the type of work you're doing can be applied to those sort of things?
I think so. I think the work that we're doing here is very foundational in leveraging multiple disparate technologies in new ways. And we're using networking as a primary application domain that is very relevant. But the foundational elements and ideas behind what we're doing can absolutely be applied to other contexts like that. And as the amount of information and online infrastructure grows at such an expounding rate, these sort of techniques will become essential in thwarting things like that.
Yeah, and for sure. By the way, I didn't mean to put you on the spot. I think we all understand that these are the fundamental, the real foundational elements that maybe can be built into these systems. But it's interesting that they're relevant. There's a pressing and real world, need for the development of these type of techniques. Yeah, excellent. That's really that's great. Thank you. Does anybody in the room have any questions for Jared? Excellent. Well, look, hang tight with us, and again, I think at the end we might have a few minutes for a little group Q&A and a little group discussion. So thank you very much. Well, that sounds good, folks. Hold on, we're going to move on and completely change. Well, not completely change topics. It turns out that this next topic is an astronomy and astrophysics project. But there's a significant amount of computer science and data analysis involved. So actually, I think our group, even though we have what seems like very varied topics, I think there might be a common theme between the groups. So we're happy to let's move on to our next presentation, which is going to be by Riley Monsrud, who is a physics major here at the University of Oregon. And turns out I know a lot about Riley because he's working in my research group. And so Riley, prepare yourself for some questions, buddy. And oh no, again, let me not pick on him too much. But Riley is going to talk about a project that we've been working on with Pine Mountain Observatory. And the title of Riley's presentation is Determining the Physical Characteristics of the Asteroid 572 Rebecca through analysis of its light curve. And Riley, can you share your screen? Are you technically prepared?
Yes.
It sounds great. Take it away, sir. We'll reset the timer right now. You got 15 minutes.
Okay, let me see. Share my screen here. Let's do that one. Okay.
Oh, great. We can see it. Oh,
okay.
We got you.
Okay, good. Okay. Hi, my name is Riley. I'm an undergraduate physics major, my 4th year here at UO. And I'm excited to bring you guys a presentation about kind of the work and projects we're working on at Pine Mountain Observatory. So this is one of them that we've been working on for, I'd say 2.5, 3 years now, around there. So yeah, let's give you guys an update on things we've been working on. So to make this a little bit easier to digest, I broke it into PowerPoint slides for each section that we have on our poster. And yeah, feel free to ask questions at the end of the presentation. So up first on our poster is the abstract. So to summarize it into key points, I would say that in August 2020, we observed the asteroid 572 Rebecca from Pine Mountain Observatory. And over the total of 3 nights and 8.5 hours, we took 605 images of the target asteroid, which we then analyzed to measure the individual brightness values of each individual file to produce a thing called a light curve, which is just a measurement of brightness over time. And from the structure of that light curve and the amplitude, we were able to make a semi-accurate 3-dimensional model of 572 Rebecca based on the published data. So the first point in the poster is talking about Pine Mountain Observatory. So PMO is located in Bend, Oregon. It's been in operation since 1967, and it's owned and operated by the University of Oregon. And so there's a total of 4 telescopes up there right now, with the newest being what's named the Robbins telescope. It's this clamshell dome with a 0.35 meter telescope in it. And this is what we use to get research grade data on asteroids, galaxies, and nebula. And as a forward look, one of the things we're working on installing in the next year or so is a 5th telescope that's going to be a dedicated helio telescope to look at the sun. And one of the interesting things we're going to do is provide live images of the sun to the UO campus through the science library on the Viz wall. So we're going to have live images throughout the day posted there in the near future. So a key point, the second point on the slide, on the poster, is where are these asteroids that we're observing? So 572 Rebecca lives in the asteroid belt. That's between Mars and Jupiter, roughly 200 million miles away. So it's pretty far out there. But one of the interesting things that might not be apparent is that 572 Rebecca is about 30 kilometers wide. So if you think in terms of Pacific Northwest terms, that might be 3 or 4 Mount Hoods wide, maybe 2 or 3. So it's a big object that's just floating out there in the asteroid belt. And speaking of the asteroid belt, asteroids are commonly thought to be just rocky remnants left over from early solar system formation about 4.6 billion years ago. And some other miscellaneous interesting facts are that 572 Rebecca was identified in 1905. So we've known about it for about 100 years, and in that 100 years, we've made a bunch of observations about it, including its composition. So it's labeled as an XCD type asteroid by the Tholen taxonomy system, which just indicates that it has a high carbon composition and low albedo measurements. I think that's good for that. And then our third bullet point is kind of the theory, like, why would you want to look at asteroids out in the asteroid belt? So one of the interesting things is that when you're looking at it through a detector, it looks like a sphere, but it's not necessarily a sphere. A lot of the asteroids in the asteroid belt are kind of more potato shaped or hot dog shaped, as you could say. And this is due to the rotation period of the asteroid being really, really fast. So on the order of 4 or 5 hours, something the size of 2 or 3 Mount Hoods can rotate. And it's pretty interesting. So in terms of physics, you could think that the centripetal force that the asteroid has when it's spinning around so rapidly kind of deforms the asteroid as it moves through the sky. So you can maybe think of it as maybe a demo here inside the stapler. So as the asteroid's tumbling through the sky and it's deforming, there's points where it has higher surface area and it's reflecting more light, demonstrated in this figure here. And there's also points along its tumble where it has lower surface area, so it'll reflect a lower amount of light. And this is a really predictable pattern that goes on for the asteroid. And this allows us to infer characteristics about the asteroid based on how much reflected light it gives off. So again, you can look at figure 4 here, kind of the sinusoidal nature of this tumbling And yeah, a lot of these asteroids have the characteristic of being more seen as rubble piles instead of one big mass. So the gravity is loosely holding these rocks together as well. Then I can go to the next one. So how do we analyze the 605 images that we got? So using a program that's widely used in the amateur and professional astronomy community named MPO Canopus, we measured the brightness of the asteroid in each frame individually using something called relative aperture photometry. So in figure 5 here, you can see we put 3 apertures around the asteroid. And the first aperture works to measure the total brightness of the source. And then the second and third apertures work to measure the sky background. So that helps with correcting for atmospheric conditions, light pollution, and a whole host of other noise-related consequences. And this sky background is just subtracted from the total source value of the asteroid. So it gives us a good gauge of the relative magnitude that the asteroid is giving off due to the reflected light from the sun hitting the asteroid. So it's important to distinguish that these asteroids aren't giving off light. It's more of a big mirror out there that's reflecting the light from the sun. And one of the things that we found while we were doing this is that there's a few limitations to this process as well. So in figure 6 here, you can see kind of a short GIF of one of the nights we observed the asteroid. You can see it moving here in frame. And you can see it comes into what's called an occultation with another star, where an occultation is just a lining up of both the star and asteroid to the point where they just mirror or overlap each other. And it's hard to do relative aperture photometry during that because the star passes within all these apertures that we set up. So there's a huge section of data on one of the nights that we couldn't count into our light curve. And so another way that we use to remove atmospheric effects is comparing our asteroid here to 3 different stars of known magnitudes in the field to remove a lot of the noise that all the stars see at the same time. So as the asteroid is moving through the sky, there's a bunch of background noise that affects each of the comparison stars that we use. And looking at this graph, you can see throughout the night, the comparison stars got brighter as the asteroid approached the horizon. And we're able to remove a bunch of those effects on the asteroid by subtracting the known constant brightness of the comparison stars from that. So we can go, that's good for that. So, and then along with that, we worked to quantify what's called an extinction coefficient to further calibrate the data, where an extinction coefficient is the measure of the change in magnitude due to what's called air mass. And air mass is the amount of atmosphere that we're looking through at any given time. So we attempted to make an estimate for the extinction, but we're not able to use the same relative photometry technique for this calculation. And the data of the August 2020 observations that we made were not absolutely photometric due to the forest fires in the area for that week. And in this table, you can see the comparison stars we used, their relative constant magnitudes, and their locations in the sky. And now the fun stuff, the results that we got. So you can see the light curve that we produced with the 605 files of brightness or individual brightness values. So each point on here is a 1/32 exposure that we calculated the brightness for. And you can see in these 3D models of the asteroid that we created are fairly interesting. It's not a spherical object like a basketball that you might think. actually has some structure to it. So this is one of the things we've been able to work on the past few years, to kind of test run the idea of getting this data and both applying it through three-dimensional models and programs. I guess one other thing that I might have skipped over is that we identified that the rotation period is about 5.591 hours for 572 Rebecca, which comes within, I believe it was 0.1 hours of the listed published value. So it's really easy to recreate the professional findings of professional astronomers that observe these. I think that's good for that. So then just a general overview / conclusion of our project here. This is a continuing project that we were working on in a collaboration with Kobe University in Japan. And the idea being behind that is that when the asteroid 572 Rebecca, say, sets on the horizon, the time shift at Kobe, Japan is enough that when we are unable to continue observing the asteroid here, the people in Kobe, Japan can pick up the asteroid and continue the observation. So we've been calling that concatenated observing. And yeah, I think that's kind of where we're at for one of our Pine Mountain projects. And if you guys have any questions, feel free to shoot them my way, even about this project, or maybe even more general to Pine Mountain as well. Yeah, thank you.
Thanks, Riley. And 13 minutes and 40 seconds. Thank you so much. Gosh, you folks are just right on time today. That makes moderation real easy. Riley, thanks a lot. And again, I hope that the folks watching can see that even though we moved from a deep dive in network traffic and algorithms to an astronomy project, again, the common theme is that we're working with data. And how does one analyze the data and draw conclusions from data? And that's an ongoing theme. And I would say one thing here at UO, we're very excited about that. And as a matter of fact, right now we're developing a new major called data science. And within that major, there are different concentrations, including one in physics. And so I just know that the Department of Physics is deeply working on that sort of thing too. Well, Riley, thanks a lot. I really appreciated hearing the summary. Like I said, that I heard it before, but it was nice hearing it again. I actually got two questions for you, and that is, is there any hope that this might develop into something that's again kind of real-time analysis or something like that?
Yes. I guess I have two answers to that. One of the things that we're working on currently, along with the solar telescope, is we're making a remote observation station in Willamette Hall, so that we can, through the internet, control the telescopes from University of Oregon and patch into the telescopes that are in Bend, Oregon. Mm-hmm. So we can, in real time, say the telescope's over in Bend, we can start analyzing the data as soon as it gets over to us over here. And another, I guess, point to that is that my second point is that the programs that we're starting to use are really good at automating the aperture photometry. Yeah. Whereas before we were manually looking at each of the individual files and putting them in spreadsheets, and looking at 605 files, that might take 12 hours or so to manually calculate the brightness levels. But we're starting to get fluent with programs that work to automate that feature. Mm-hmm. So that's one of the improvements of the project we've made, and it's kind of a proof of concept right now.
And again, dare I say, an interesting parallel to time improvements, hearkening back to Jared's presentation, excuse me, increasing efficiency and how one can make these processes run quickly and more accurately is extremely important. And again, I promised the audience, we didn't know this was going to happen, but an interesting parallel between these projects where this idea of efficiency and being able to do things, parallel processing and this sort of thing is highly applicable to many different facets of science. And then I want to make a quick comment too, because Riley said something interesting about the forest fires. And then it turns out that when we were making these observations was on the tail end of when we had some bad forest fires last summer. And as you might imagine, folks like forest fires, well, what does that have to do with asteroids? Well, guess what? To observe the asteroids, we have to look through the Earth's atmosphere. And when the forest fires were around, there was a lot of smoke and small particles in the atmosphere, and that changes the colors and the way that we had to observe. And so down with forest fires, but it did present us with an interesting issue to deal with in this particular data set. And so that's why if you scratched your head and you thought, what does a forest fire have to do with the asteroid? But what we was thinking that is, again, pretty neat. We got efficiencies all over the place, and pretty interesting to think that we can. There's a 20-mile wide rock 200 million miles away, and observing it with a little old telescope up on Pine Mountain, we can determine what its shape is. So go students, go research. Well done, Riley. Thank you very much. And please hang out and let's see if we can get a little Q&A going at the end of the session. Thank you very much, sir. And so let's move on. I mean, look, I'm ready to go. And Lucy, you're up next. Lucy Roberts is actually, let's see, what's your major, Lucy? I'm not sure.
I am actually, so I'm a spatial data science and technology major, moving into also a data science major.
Oh my gosh, I promised that was unscripted. She didn't even know I was going to say that stuff earlier about data science. Well, look, thank you very much. And what year are you in?
I am in my second year. I'm giving a presentation though on the research I did my first year.
Yeah, okay, good deal. So you have some time to move into the new major, and also, so you've got a little time left to develop their projects and your skills too. Well, look, that sounds super cool. Lucy is going to talk about a project that's named Quantifying Glacial Melt and Movement Using Remote Sensing in Greenland's Summerlik Fjord. And you can, of course, you can hammer me for the pronunciation. But Lucy, okay, take it away. You got 15 minutes.
Wonderful. Thank you so much. And just before I begin, I'd love to give a shout out and thank you. Dr. Fisher was very involved with the North Star project, which I participated in my freshman year before I started class. And that was the reason that I got involved with research my freshman year, as opposed to, I don't know, later on in my career.
You're most welcome. Thank you so much. North Star is awesome. If anybody doesn't know about northstar.uoregon.edu, go check it out.
Just plugging it, gotta rep it. There we go. Okay. But yeah, I'm going to be talking about my summer research from this last year, if it's going to let me present, on quantifying glacial melt and movement using remote sensing in Greenland's Summerlik Fjord. And I also have notes on the desktop above me, so pardon me if I'm not looking directly at the camera while I'm talking. But as just a general background, as global climate change leads to the warming of polar regions and recession of glacial bodies, fresh water from glaciers is discharged into the salty, briny fjords and oceanic waters in places such as Greenland that have large quantities of glaciers. And so as such, it's important to be able to understand and quantify how icebergs melt and where that fresh water gets distributed spatially. As a background, this is a Landsat imagery of Hellenheim Glacier. Landsat is a satellite system that orbits the Earth and takes images of the entire Earth every 2 to 3 weeks. And so this is the Hellenheim Glacier in the Summerlik Fjord area where I was looking. And so this first image is from late August in 1972, I believe. And the second image is from 2019. And so in comparing these two images, you can already see to what degree these glaciers have begun receding. If you look here, this is the glacier feeding into the area. And this is called the terminus. It's where the glacier meets the kind of salt water. And this is where the glacier breaks up into icebergs and gets divided into what's called the melange. And then as our icebergs move through the melange, they enter the fjord region. And from there, they either break apart or enter into the ocean. And so Dr. Fisher had been mentioning lots of parallels between everyone's research. I think it's fun because you guys are using stuff on Earth to make guesses about stuff out in space. And I'm using stuff out in space to make guesses about what's going on here in the Earth. So with that said, our research question was, how has iceberg movement and melt on tracked icebergs in Sirmilik Fjord differed year to year? And this is because Dr. Sutherland from the Ocean and Ice Lab had been going out every year between 2012 and 2019 to put GPS tracking units on some of these icebergs and use them as proxies to quantify and monitor oceanic currents and how these icebergs travel throughout the fjord. And a previous study published had congregated this data from 2012 to 2014, but we hadn't really looked at all of those years together before. And so it was my goal in my summer research to kind of come up with a couple of characteristics that we could generate about each of our GPS tracking units individually, as well as kind of generalizations year to year about how those icebergs moved in the various regions in the fjord. In terms of methodology, initially my exploration of the iceberg data began with loading the data structures from various years into MATLAB and coalescing them into a single data structure, which we could use to compare interannually. And so this allowed me to create some pretty simple graphics that could compare interannual movement of our icebergs. For example, this is the distance traveled over the time in weeks since May. And so in this image, the y-axis is constant in terms of distance traveled, but the x-axis is not, because you can see there's a lot of variation interannually. In 2016, for example, the GPS units were deployed in the very beginning of May and very high up in this melange region. So many of them did not end up exiting that area. Actually, any of them in 2016. In 2019, for comparison, all of our GPS units were discharged in about late July, and they therefore were able to travel farther. They were also discharged later on in the fjord, and so they ended up actually exiting the fjordic region and making it all the way down around the tip of Greenland and up on the other side. And so you can see here kind of how these different characteristics of the different years are really brought to life in these images. And there are some spots where you can observe, for example, in 2013, you can see this kind of jump in the velocity of the travel times of the icebergs. And that is because as the icebergs are exiting the fjord, they reach this shallower region where the current has to move faster and it pushes them forward faster. So they're good vectors of the current flow and being able to keep an eye on the currents there. Halfway through the summer, we transitioned into using remotely sensed imagery to then try and quantify how those icebergs were melting as they moved throughout the fjord. So we were looking at satellite imagery from Landsat and Sentinel programs, which are funded by NASA and the European Union, respectively. And so what we could do then is, since our GPS units reported on average about once an hour, they report less as they start to lose, as they start to get older, we could then take the GPS points from around the time that these images were taken and try and identify and pinpoint where our specific icebergs were. So this image is a very clean example of one time when the GPS units fairly decently lined up with where the icebergs that they were representing were at that time. And so I would go through the databases that have the Landsat and Sentinel footprints and compare them to where our GPS units were at that time using the footprint that was on there. And you just have to manually inspect and see if your GPS units approximately fall within the footprint of the satellite imagery at that time. If they do, then you download the image. Each of these images is at about 30-meter resolution. So every pixel represents about 30 meters of land. So these are huge images. Each image is over a gigabyte worth of data. And so they're contained in 8 different bands of data that represent different measurements. For example, bands 2 through 4 are red, green, and blue, which allow us to have images in color like the one you're looking at here. And those are at a 30-meter resolution. Once I had identified an image I wanted to use, I could load that image into QGIS. And if you're not a huge fan of geospatial software like I am, QGIS is our open source version of geographic information systems. And so I ended up using band 8, which is the panchromatic or grayscale version, and it is at a finer resolution. It's at a 15-meter resolution. And so then I could go in and manually trace out the area of the icebergs that we were tracking. Our goal was to get about 2 to 3 images for each iceberg, depending on how long they were deployed and what the cloud cover was like in that year. Once they're loaded into QGIS, QGIS has this incredible plugin called the semi-automatic classification plugin, which allows for you to rectify the visual imagery, because as the satellites are pointed at the Earth, like Dr. Fisher was mentioning, they have to go through all of these layers of atmosphere. And so things such as cloud cover, the angle that the sun is at, the brightness of the sun in that day can visually distort the image. So the semi-automatic classification plugin allows for you to minimize that distortion and then to trace out the perimeter and draw the diagonal to see how large the iceberg actually is at that point. Over the summer and during my time doing that work, I was able to develop a workflow for identifying remotely sensed icebergs connected to GPS units and begin populating a spreadsheet with preliminary data on surface area and average travel times through different areas of the fjord for each of our years. We were also able to, during that first section, quantify and visualize interannual differences between GPS data that was impacted by when the GPS units were deployed, as well as the characteristics of that year. Future directions for this research can include integrating other satellite imagery to create a finer temporal scale. Imagery, such, for example, as I'm right next to a train, so I'm sorry if it's getting a little loud right now, but imagery such as those operated by Planet are at, I believe, 5-meter resolution or 1-meter resolution, so very high level of resolution, and also taken at a much more regular temporal scale than those by Landsat and Sentinel. And so I did have some meetings with people from Planet trying to get access to that for free. Turns out satellite companies don't like to give you their product for free, so that didn't end up working out in the time that I was doing this research. And then also applying this workflow to other fjords in Greenland. For example, the Ocean and Ice Lab deploys GPS units in Jakobshofen Fjord, which is in West Greenland. Those GPS units tended to be deployed for a shorter period of time, so they didn't match the temporal scale I was working with and was limited by from the Landsat imagery. And I just want to give a special extra shout out to Dave Sutherland and Nicole Beeb from the Ocean and Ice Lab for mentoring me and helping me throughout the last year. And then the University of Oregon Center for Undergraduate Research Experiences for hosting this undergraduate research symposium, but also funding me through the first year undergraduate research experience fellowship and continuing to support me in applying for and looking at research positions through the last year as well.
Thanks, Lucy. Super interesting. And again, love the connection to the previous talks. Again, there's a parallel, there's a thread going through the discussions today. I'm fascinated. I love satellite imaging in a slightly different universe. I'm not an astronomer looking up, but I'm a satellite studier looking down. So I really appreciate that. I have to add, I got a whole list of questions for you. Are the icebergs that do any of these end up presenting dangers to shipping lanes or anything like that, or are they close enough that you don't worry about that so much?
The icebergs that we were looking at did not necessarily. They tend to cut off and get broken off at the shelf. I don't know if you've looked at Mark Carey's research at all, but he actually has this. I've had a couple guest lectures with him, and he studies the war against icebergs in near Greenland, especially in the early 20th century.
Yeah.
And it's fascinating. I mean, they were actually trying to blow up these icebergs.
Yeah.
So that's not related to the icebergs I was working with, but yeah, some of those ones from 2019 could
they could
absolutely
yeah.
be considered that. Yeah.
And what is, speaking of sort of that, what is the typical size of the objects or the bergs that you all are interested in or start studying?
Yeah, and that is something that the number has slipped my brain currently. I transitioned out of this lab at the beginning of this year, and so
gotcha.
Going through
even just ballpark. I mean, are these tens of miles big?
Yeah. These ones, like the square one that I was showing you, I think that one was about a mile by a mile.
Okay, so these are sizable chunks.
And that was the reason that they were selected to have the GPS units on them, is they had to be big enough to support them flying out in a helicopter and basically dropping down and
literally putting the unit on the ice.
Yeah, or dropping one down. Yeah, and it had to be big enough that it's not going to break up or flip over.
Yeah,
that's how we use a lot of our GPS units.
Clearly, and so these are big, but maybe not in comparison. For example, in the news the last couple of weeks, there's the largest iceberg ever broke off, an Antarctic ice shelf, and that's like the size of Long Island or something. So these are not, these aren't the monsters like that, but still quite sizable. Yeah.
These can be quite large, and I also am scared that I'm giving you the wrong numbers now, so I'm gonna.
That's just. Well, let me ask you one more question, then we'll leave you alone. Can you envision, continue, this type of project goes on for the next, to call it 10 or 20 years. Can we then use this data to help us look for trends, in the sense of, are there more bergs per year? Are they traveling in different ways? That sort of thing.
Yeah, and that's what I was hoping to look at in general with kind of coalescing all of these years together.
Gotcha.
I think, some of the limitations are that they are deployed at different times in the year. There's a lot more noise and variation when it comes to annual oceanic events in comparison to events that would occur due to climate change or something like that.
Yeah, gotcha.
One of the older papers that the lab published, and I used a lot of her workflow their workflow to kind of develop this one for our specific icebergs, is using the same satellite imagery, but then tracing out each of the individual icebergs in the fjord and trying to see how much mass is lost as they travel out.
Gotcha.
And I think having a larger sample size like that is a lot trickier, but might be a better.
But the idea is more data is better in some sense. and I mean, to complete and of course, folks are always like, you scientists, you always want more data. Well, yeah, but there's, typically, of course, there's reasons for it. In the case of yours, again, higher numbers, you can track more of them. Even back, as Jared said, more priors and more, more data to work on generally is better. And of course, for the asteroids, the same thing. The more data that we get, the better precision we can have with making the predictions about the curves and the shapes of the asteroids and things too. Well, look, that is fascinating. Thank you very much. Again, the diverse topics, but love the parallel of looking up and looking down at the same time. Well, very nicely played. Thank you very much for that. So, well, look, folks, we're going to move on. We've got one more presentation, and this one's a little bit unique. We have this is a parallel project that is that worked with Riley's the project that he discussed with our asteroid observations, and we have one of our collaborators from Japan is here with us. Nobuyuki Tamai is a student and is the lead student who's working on our project on the other side of the world. So Nobuyuki, welcome. Very nice to see you today.
Hello. It is 3:45 in Japan, so I'm sleepy. But
yeah, no, we get it. And this is right. And Nobuyuki, it is 3 o'clock in the morning, and Nobuyuki has come to help present us. But we're going to do a little bit different. Is Nobuyuki has provided a voiceover for his poster, and it's 5 minutes. And Riley is going to help and show us that, so we can just watch and listen for a couple minutes, and we'll come back and have a little discussion about the poster. And so, Riley, if you can help us with that, that would be wonderful, sir.
Okay, let me know if you can't hear audio.
Yeah, go ahead and hit play once. Let's see.
Results of coordinated observations of
That sounds good, but turn it up if you can.
the bin by Pine Mountain Observatory and Nishiharima
You're good.
Astronomical Observatory in August 2020. Asteroids are small astronomical objects orbiting the Sun. They are thought to be leftovers from the planet formation process. So, study of asteroids can give us information on the planet formation and the early history of the solar system. Pine Mountain Observatory, located in Central Oregon, is the observing station of the University of Oregon. Nishiharima Astronomical Observatory, located in Western Japan, is an astronomical observatory of the University of Hyogo. To reveal the shape of an asteroid, it is necessary to determine the light curve, which is time variation of the brightness. Coverage for more than 2 rotation cycles is necessary for accurate determination of the rotation period and light curve. However, for asteroids that have a rotation period longer than several hours, it is difficult for one observing site, and multiple observing sites that are separated by 6 hours in longitude are needed. Pine Mountain Observatory and Nishiharima Astronomical Observatory match this requirement. You can see the pictures of the 2 observatories in Figure 1 and 2. The target of our observation was an asteroid 665 Zabin. It is the main asteroid belt between the orbits of Mars and Jupiter. The orbital period is 5.58 years, and the rotation period is about 4 hours. Although we attempted successive observations at Pine Mountain Observatory and Nishiharima Astronomical Observatory, the observing condition did not allow us continuous coverage. The observation at Pine Mountain Observatory was on August 16, and the one at Nishiharima Astronomical Observatory was on August 24, 2020. Combining the data from the 2 observatories, we were able to determine the light curve of 665 Zabin for the complete period of the rotation. It is shown in Figure 4 in the poster. Phase matching analysis gave the rotation period and modulation amplitude, which agreed well with the known results. We were able to reconstruct the 3D shape model of the asteroid from the light curve, which is shown in Figure 5. Our result demonstrated coordinated observations by the 2 observatories are effective in determining the light curves and rotation period of asteroids that have rotation periods larger than several hours. The analysis procedure is also established, and we are planning a project to observe more asteroids and contribute to the asteroid database. For more details, please take a look at our poster. Thank you very much for your attention. I can enlarge the poster in this screen, so if you want, please ask me.
I think you're muted. Yeah, Dr. Fisher, you're muted.
Thank you. Nobuyuki, thank you for the voiceover. That was very good. We appreciate the submission. I have a question for you.
Yes.
Did you get to go to Nishiharima to make the observations?
Yes. I went to Nishiharima Astronomical Observatory to observe 665 Zabin in
August of 2020. Yes. Yeah. And did you was it one night of observations or 2 nights? I think 1 night maybe.
Yes, 1 night.
1 night, yeah. And if I remember, we 50% of the night was good, but then some clouds, a little bit of clouds.
Yes, 60% of night. Do you mean the weather is good?
Yes, the weather was partially good and partially bad.
Yes, I'm proud of the weather. 6% of weather was good.
Excellent. And let me ask you one more question. Do you think we will be able to do more observing in the future?
Yes, in the sky, there are many asteroids which have rotation period larger than 1 night or 6 hours. So we can combine the observations and analyze the data.
I think so too. We look forward to continuing the partnership. And Nobuyuki, what year are you in your studies? Are you early in your studies, or are you ready to graduate?
Sorry, I can't.
Did you just start studying at university? Are you a new university student?
No, I'm a third year student in Kobe University.
Excellent. So we will be able to observe with you next year also. Yes. Thank you very much, sir, for your contribution. We love the international collaboration is wonderful. We are very happy to have you take part.
I'm very happy too.
Thank you, sir. Well, look, everybody, so there's the end of the presentations. I wanted to open the floor up just for a couple minutes for if any folks have questions for each other or any just general comments. I wanted to say again, just thank you to everybody. I think this shows the level of sophistication that our students are working at. These are great projects. These are heady projects that have a lot of potential for future work too. And I think that it's great to see the current generation of UO students and ducks that are setting up for the future generations too. And so thank you very much. And let's see, do you have any pressing questions, anybody? If not, yeah, Lucy, what you got?
just noticed I checked the YouTube live stream and someone had asked
Yeah.
what factors determine asteroid shape?
That's a good question. Riley, do you have an idea?
Off the top of my head, no, not right now.
That's okay.
Not that I can think of.
Let me help a little bit with this one, because it turns out it's actually that's a really good question. The one thing that we are interested in is, if you remember, both Riley and Nobuyuki mentioned that the rotation periods for the asteroids we are interested in are pretty short, 5 hours or so. And remember, this is an object that's as big as 2 Mount Hoods smushed together, 2 Mount Hoods, and that thing is spinning on its axis in 5 hours. And so that's really, they spin quite fast. And as you might be able to imagine, as objects spin, they get flattened because of that. And that's what we're interested in. We're looking for asteroids that are spinning quickly, that might be a little bit flattened, and that would let us know that they are not a solid rock, but they are many, many, many rocks that are pieced together, held together by gravity, what we call a rubble pile. And so, by the way, there are other things that determine the shape. For example, maybe the asteroid had a collision with another asteroid back in the past, and that can alter the shape. But that's a hard question to answer. But we're most interested in the rotation. So thanks, Lucy. Thanks for sharing that. Well, look, everybody, we're going to turn you loose. It's about, we're just a couple minutes early, but that's okay. I'm going to hang out here in the room for a few minutes in case anybody wants to chat, but we'd like to formally close the session. And really thank you to the presenters. Laura, thanks for helping on the technical side. Jessica Winders, Kevin Hatfield for running the URS, and everybody who's been involved. We're looking forward to maybe next year being back a little more in person, but we really appreciate having all of this stuff archived. Share the links, share the YouTube link with everybody, and let's see, let's make sure that we can share the knowledge and the research that we've produced. Thank you, everybody. Go Ducks, and we'll talk to you soon. Bye-bye. Laura, I'm not sure what the procedure is. If you're the one who can kind of stop, or maybe Jessica does.
All right, we have stopped recording.
Yay!
Yay!
That was great. No, thank you all.
Awesome.